So in this video, we're going to look at how the mole relationship comes into play in a chemical reaction. And so what we're going to do is we're going to use what's called a mole-mole factor from a balanced chemical equation to calculate the number of moles of another substance in the reaction. And then later, we're going to use this number of moles to calculate masses in a chemical reaction. And this whole process that we're going to look at is a quantitative relationship between the amounts of reactants consumed and products formed in chemical reactions, and it's expressed by a term called stoichiometry. When we looked at Chapter 3 that dealt with matter, I discussed the law of conservation of mass. And the law of conservation of mass indicates that in an ordinary chemical reaction, matter can be created nor destroyed. So there's no change in total mass that occurs. And the mass of the products is equal to the mass of the reactants. So we're going to apply this term called stoichiometry. Let me write it for you. So we're going to look at mole relationships in a balanced chemical equation. So here we have the balanced reaction that shows the tarnish of silver. So that we have silver metal and sulfur, and then we will form silver sulfide. So when we balanced our chemical equations, we saw that the coefficients in an equation represent numbers of molecules. Because moles are proportional to molecules, the coefficients in an equation also represent numbers of moles. So let's look at this balanced chemical equation. What it's saying is that we have 2 moles of silver reacting with 1 mole of sulfur to form 1 mole of silver sulfide. If you look at the mass of the reactants, the mass on the left side of the equation equals the mass on the right side of the equation. And what we're going to see at the end of this video is that we can use moles and the molar mass to determine these amounts. So again, let's just look at what we have from our balanced formula, our balanced chemical equation. We have our equation up top where you have silver reacting with sulfur to form silver sulfide. What the coefficient says is that there are 2 silver atoms reacting with 1 sulfur atom to give you this new molecule, silver sulfide. If you were to multiply the whole chemical equation by 100, it could be 200 silver atoms plus 100 sulfur atoms, giving us 100 silver sulfides. All this table is showing you is the different types of ways that we can interrelate the terms in this chemical equation. All right, so let's look at this chemical equation. We have iron reacting with sulfur to form iron 3 sulfide. The equation is balanced, and if we look at this, this means that 2 moles of iron react with 3 moles of sulfur to give us 1 mole of product, our iron 3 sulfide. We can use a balanced chemical equation to write conversion factors, and this conversion factor is going to be called a mole-mole factor. And it's a ratio of the moles for any 2 of the substances in an equation. So if we wanted to look at the mole-mole factor for iron and sulfur, it would be 2 moles of iron per 3 moles of sulfur. If we wanted to look at the mole relationship between iron and the product iron 2 sulfide, we could write 2 moles of iron to every 1 mole of product, or 1 mole of product to every 2 moles of iron. And finally, sulfur to product as well. We can use these mole-mole factors in later calculations. So here in this learning check, we need to consider the following equation, where we have 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas to form 2 moles of ammonia gas. So you need to choose the correct mole-mole factor for each of the questions. So let's look at A. It says a mole-mole factor for hydrogen and nitrogen is. So there are 3 moles of hydrogen and 1 mole of nitrogen. So the correct answer would be 2. The next B says a mole-mole factor for ammonia and hydrogen. Okay, so there's 2 moles of ammonia. So the correct answer, again, would be 2, where you have 2 moles of ammonia to 3 moles of hydrogen. All right, so let's look at an example calculation with mole factors. The question says, how many moles of iron 3 oxide can form from 6 moles of oxygen? So let's check to make sure our equation is balanced. On the left we have 4 irons, on the right we have 4 irons. And then on the left we have 6 oxygens, and then again we have 6 oxygens on the right. So we're balanced. So the question is saying how many moles of product can form if we have 6 moles of oxygen to start with. So what we need to do is write our conversion factor. So this is like any conversion factor problem. You're going to have your given, which is 6 moles of oxygen. Then we're going to use our conversion factor. When we're doing these types of calculations, I've said put your given as the first term. Generally, that should be your strategy. And then in your last term, you need to have the desired unit in the numerator. So our conversion factor is going to be for 3 moles of oxygen, we get 2 moles of the iron 3 oxide. So our moles of oxygen will cancel, and we're left with 4 moles of the iron 3 oxide. All right, let's try a learning check. How many moles of iron are needed for the reaction of 12 moles of oxygen? Pause your video and set up the calculation. So you see here I wrote down our given is 12 moles of oxygen. The conversion factor that we're going to use is 4 moles of iron per 3 moles of oxygen. Again, you want your desired unit to be in your numerator. Your moles of oxygen cancel, and your answer is 16 moles of oxygen. And just to tie back to everything that we've been doing, there are 3 significant figures here, so your answer needs to have 3 significant figures. Okay, so again, this is how the textbook lays it out with your table, and then how to solve the problem through your mole-mole factor. These are your 2 conversion factors, and then finally how they cancel to get answer C, 16 moles of iron. Now what we're going to do is we're going to take this one step further. We're going to use moles and molar mass to do some mass calculations for chemical reactions. So the learning goal here is given the mass in grams of a substance in a reaction, calculate the mass in grams of another substance in the reaction. So in our mass calculations, when we have a balanced chemical equation, we can convert the mass of one substance A to another substance B by first converting this mass of substance A to moles using the molar mass. Then we can convert moles of substance A to moles of substance B using the mole ratio of B to A. And then finally convert the moles of substance B to grams using the molar mass. So all of these calculations are going to involve our mole conversion factors and the molar mass, which we looked at in a previous video. Suppose we want to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen in the following equation. Let's check to make sure our equation is balanced. On the left we have 2 nitrogens, on the right we have 2 nitrogens. On the left we have 6 hydrogens, and then on the right we have 6 hydrogens. So our equation is balanced. So first what we're going to do is write down what's given. That we have 32 grams of nitrogen. We need to find out how many grams of ammonia are going to be produced. So I rewrote that we are given 32 grams of nitrogen. We can determine the molar mass of N2 by using the periodic table. The atomic mass of nitrogen is 14.01 AMU. So we have 2 nitrogens, so that would be 28.02. Now when we're doing the molar mass, it's grams per mole. We can also determine the molar mass of ammonia. Equals 17.03 grams per mole. Alright, so now what I'm going to do is I'm going to take all of this information and I'm going to use it to find the grams of ammonia produced. Well, we start with 32 grams of nitrogen. When we look at this equation, it's giving us the ratio of moles. So what we need to do is we need to take this mass and convert it to moles. We can't just use that mass and the coefficients to determine the mass of ammonia produced. We have to use the moles and the molar mass. Okay. So I have my 32 grams of nitrogen. When I multiply that by the molar mass, where I have 28.02 grams of nitrogen per 1 mole of nitrogen. Then I'm going to use that mole factor, where 2 moles of ammonia per 1 mole of N2. I get that from my chemical equation. Then what I'm going to do is I'm going to use the molar mass of that ammonia. And what you'll see is that my units cancel and I'm left with a desired unit in the numerator. So my grams of N2 cancel, my moles of N2 cancel, my moles of ammonia cancel, and my moles of ammonia cancel, and I'm left with that unit. So it's just one big dimensional analysis problem, or conversion factor problem. So let's multiply and divide everything out. So let's go through and multiply and divide. So it's 32 divided by 28.02, times it by 2, times it by 17.03. And our answer is 38.89 grams of NH3. We need to have 2 significant figures, so it's 39 grams of NH3. So here, it's just stepping you through the problem, giving you a little schematic. Okay, here are your conversion factors that you need. This is your molar mass. Okay, here's another molar mass. And this is your mole-mole conversion factor. And here's the calculation set up nice and neat for you, where all of your units cancel and we get our 39 grams of ammonia. All right, here's a learning check. How many grams of oxygen are needed to produce 45.8 grams of iron 3 oxide in the following reaction? All right, so pause your video and see if you can set up the calculation. All right, so I wrote down what's given. We need to find the mass of oxygen in grams. All right, so again, this is just one big conversion. Start with what's given. And if you label your units well, everything should cancel out and help keep you organized. So I have given my mass of product. I multiply by the molar mass of that product to find out its moles. Then I can use my mole conversion factor, that there are 3 moles of oxygen per 2 moles of Fe2O3. And then finally I can multiply by the molar mass of oxygen, okay, so we'll see my grams of iron oxide cancel, iron 3 oxide, my moles of iron 3 oxide cancel, and then my moles of oxygen cancel, so I'm left with grams of oxygen. And when you multiply and divide everything out, you should get 13.8 grams of oxygen. So this slide is just laying out what we have given in our table. This is our schematic of what I wrote out. Here are some of our conversion factors and our mole factors. And then finally, the calculation. All right, here's another learning check. Same type of problem that we did before. Pause it and see if you can do it. So we have 13.1 grams of water. The molar mass of water is 18.02 grams per mole. Again, just to refresh, all you need to do is just go to the periodic table and look up the atomic mass or the atomic weight of each element in the formula and just total it up. And then you just add the units grams per mole. All right, so let's set up the calculation. We have 13.1 grams of water times the molar mass of water. And again, if you put your labels in, you'll see how everything cancels. And then we know that it's a 1-to-2 relationship. And then finally, we can multiply by the molar mass of oxygen to get grams of oxygen in the numerator. So my units of cancel, my grams of water cancel, my moles of water cancel, my moles of oxygen cancel to give me a final answer of 11.6 grams of oxygen. And there are 3 significant figures, so my answer needs to have 3 significant figures. So here's the table where everything is laid out. Here's your schematic of how to solve the problem. Here are your conversion factors. And then finally, your answer laid out how I demonstrated previously. So these are the types of calculations you'll have to do with your chemical equations. So you remember you have to learn how to balance a chemical equation. And then you have to understand what the coefficients mean. So the coefficients are going to give you your mole to mole ratios. And then when we want to convert to grams, we need to use that molar mass to convert to grams. So this concludes the lesson or the videos for Chapter 7.